Jupiter doesn't have weather the way Earth does. It has something far stranger. When we picture Jupiter, we usually imagine its colorful cloud bands and the Great Red Spot, a storm so large it could swallow Earth whole. But that iconic image hides the most extreme weather system in the entire solar system. Because Jupiter's true chaos isn't at its equator, it's at the poles. For most of human history, Jupiter's poles were a mystery. Every telescope on Earth struggled to see them clearly. Even early space probes flew past too quickly, capturing only brief, blurry glimpses. Scientists knew storms existed there, but no one expected what NASA would eventually find. When the Juno spacecraft arrived at Jupiter in 2016, it didn't orbit the planet the way most spacecraft do. Instead, it took a highly elliptical polar orbit, plunging over Jupiter's north pole, diving close to the cloud tops, then racing out over the south pole again. Juno's JIRAM instrument captured these storms in infrared, seeing through the thick, cloud-covered atmosphere for the first time. What JIRAM revealed goes beyond what our eyes can see. Deep layers of swirling winds, pockets of heat, and the invisible forces keeping these storms alive for years, possibly decades. Unlike Earth's hurricanes, which fade after days, Jupiter's polar cyclones interact like dancers in a cosmic ballet, bouncing off one another, slowly drifting and locking into place. Infrared data combined with radio measurements showed how energy flows from Jupiter's interior, fueling these storms and shaping the planet's extreme polar weather. Every flyby reveals more, a world where wind, heat, and rotation collide to create patterns that feel almost impossible, yet are entirely natural. Jupiter's poles remind us that the universe can engineer order without intention, spinning storms that dwarf everything we know, and proving that Earth is just the beginning of the story. So how does a planet create storms like this? To understand Jupiter's polar vortices, you first need to understand what kind of world Jupiter really is. Jupiter is not a solid planet. There is no surface to stand on. It's a massive sphere of gas and liquid, made mostly of hydrogen and helium, with pressures so intense that matter behaves in ways we can barely reproduce in laboratories. But Jupiter has something Earth doesn't: enormous internal heat. Jupiter radiates more energy into space than it receives from the Sun. That heat comes from slow gravitational compression deep inside the planet, leftover energy from its formation over 4.5 billion years ago. That internal heat fuels Jupiter's weather, and it never turns off. Now add rotation. Jupiter spins incredibly fast. One full rotation takes just under 10 hours. That rapid spin supercharges the Coriolis effect, the force that causes moving air to curve and form rotating storms. On Earth, the Coriolis effect shapes hurricanes. On Jupiter, it sculpts the entire atmosphere. At the equator, this creates the familiar bands of clouds flowing in opposite directions. But at the poles, something different happens. Instead of long jet streams, the energy funnels inward. Storms form. They grow. They begin to interact. And instead of merging into a single chaotic mess, they lock into place. This is where the polar vortices come in. Each cyclone at Jupiter's poles acts like a massive rotating wall of energy. When two cyclones get too close, their winds push against each other, preventing them from merging. At the same time, Jupiter's rapid rotation keeps them confined to a narrow region near the pole. The result is a delicate balance. Too close, and the storms repel each other. Too far, and the Coriolis force pulls them back into formation. Think of it like a gravitational dance, but made of wind, heat, and pressure. For years, scientists believed this kind of stable storm geometry shouldn't be possible. Most atmospheric models predicted that polar cyclones would eventually merge into one giant vortex or scatter randomly. But Jupiter refused to follow the rules. Juno's infrared instruments revealed that these storms extend deep into the atmosphere, hundreds of kilometers below the visible cloud tops. They are not surface-level features. They are deeply rooted, three-dimensional systems, anchored far below where sunlight can reach. That depth is one reason they last so long. Another reason is the absence of land. On Earth, hurricanes weaken when they lose access to warm ocean water or encounter mountains and continents. Jupiter has no land, no friction, no interruption. The storms feed continuously on the planet's internal heat, like engines with an infinite fuel supply. And then there's the scale. Everything on Jupiter is bigger, faster, stronger. Wind speeds in Jupiter's polar cyclones can exceed 300 miles per hour. Lightning flashes are more powerful than anything recorded on Earth. Some bolts stretch for miles through the atmosphere. This is weather operating on a planetary scale. But the most unsettling detail is how calm it all looks. From above, Jupiter's polar vortices appear almost peaceful, symmetrical, balanced, stable. There is no visible chaos, no obvious destruction. Yet inside these storms, the forces involved are beyond anything humans have ever experienced. Pressure increases rapidly as you descend. Temperatures rise. Hydrogen begins to behave like a liquid. Eventually, it may even act like metal. These storms are not just weather phenomena. They are windows into Jupiter's interior. By studying how these vortices move, interact, and persist, scientists can infer what's happening deep inside the planet. How heat flows, how materials circulate, and how Jupiter's internal structure is organized. This has implications far beyond Jupiter itself. Gas giants are the most common type of planet in our galaxy. Many of the exoplanets discovered around other stars are Jupiter-sized or larger. Understanding Jupiter's atmosphere helps scientists understand how these distant worlds behave and whether similar storm systems might exist elsewhere. Earth's weather is driven by sunlight. Jupiter's is driven from within. That one difference changes everything. It creates storms that don't fade, patterns that don't break, structures that look engineered yet are completely natural. Jupiter's polar vortices prove that nature doesn't need intention to create order. Heat, rotation, time. Scaled up, they produce storms that last for generations. These aren't just distant storms, they're physics at its limit, and a reminder that Earth isn't the standard, it's the exception. Above Jupiter's poles, storms larger than Earth spin endlessly in the dark. And for the first time in human history, we're watching them happen. Not in theory, not in simulations, but in real time. So if you like this video, share it with your friends and subscribe to our channel for more cosmic stories that connect you to the universe in ways you never imagined.